One. Record.
Right, good afternoon, everyone. Welcome to this afternoon's webinar. We're really pleased to have such a great turnout today, which I think is both a testament to our speaker and his topic. So I'm going to deal with a couple of admin matters before we start. I see there are still some people joining, so that'll also give them a minute or two to join in. So please keep yourselves muted through the session. You're welcome to post questions in the chat that we can go to later. Otherwise, we'll have time for the normal Q&A at the end of this talk. So there you would just raise your hand as normal, and we will go to you when it's your turn. Please also take note that the slides will be made available after the presentation, so you can all relax and focus on what our speaker has to say instead of trying to take notes or get screenshots or the like. So I'm going to keep the introduction quite short. Dr. George Karageorgis received his PhD from the University of Leeds in 2015. He followed this with postdocs both at Leeds and the Max Planck Institute in Dortmund, where he was a von Humboldt Fellow. He's been at AstraZeneca since 2020, where he's currently senior scientist. And today he's going to be discussing what is a very non-trivial topic of solvent selection for industrial processes. So over to you, George.
Hi, Kathy. Thank you for the opportunity to present, and thanks everyone for tuning in to listen to me speaking about and discussing how we do data-led experimentation on AstraZeneca, and more specifically about solvent selection to run our processes. So today I'll give a brief introduction about myself and my organization. I will discuss briefly why we're interested in solvent selection, tell you about what we do at AstraZeneca to inform our decisions about solvents, and what considerations there are before moving on to exhibiting some case studies that we managed to solve using our data-led approaches. So at AstraZeneca, we're involved in the whole spectrum of the drug development pipeline, from the discovery all the way to post-approval. We have various departments such as our oncology and biopharmaceuticals R&D that generate a lot of compounds, and they're usually used for clinical studies. Before compounds reach early chemical development and global chemical development, where more robust routes towards a fixed target are devised, and later on-market technica looks after post-approval improvements. So at Macclesfield, we're very lucky to have presence by these three departments, and I personally work in chemical development, where again, we develop the manufacturing routes and supply material for late phase trials and marketing applications. So Macclesfield, for those who don't know, is up here in England. I have the privilege of working in a building with the periodic table on its forefront. And chemistry at Macclesfield used to look like this, but it's slowly starting to look more like this as well. We aim to move with the times and adopt new technologies as they emerge and have impact. So more specifically, I would like to emphasize the importance of solvent selection. This is because the majority of commercial processes are run in solution, whether in batch or through continuous processing processes. Organic solvents are a major contributor to process mass indices and waste, and we are very conscious of what we produce as an organization. And additionally, solvents can determine chemical compatibility, reactivity, as well as material properties. And all of these are non-trivial and are hugely important to running a process. This is because we use distinct or multiple solvents per unit operation. So you might use a solvent to charge things in a vessel, another solvent to do your reaction, something else to transfer to another vessel before you do your workup or your crystallization. You might use a different solvent or solvent mixture to do washing or even change that solvent before you are able to dry your isolated solid. And whilst this is going on, our objective most of the time is to find the best solvent or solvent mixture for that operation, whilst at the same time minimizing the amount of solvents that we need to use, adhering to material specifications, and making sure that we are operating within our sustainability targets. Obviously, this is a multifaceted challenge, and all I'm trying to get at is that there's no silver bullet. Every case is different, and in order to optimize this problem, the solution to this problem, we need to make informed decisions. Obviously, informed decisions require data, and this is where we have turned our organization into a data-led decision-making process. And to facilitate that decision-making, we have built data pipelines that connect the collection point of data and reach all the way through to retrieval, interaction, and visualization. And somewhere in between these two ends, we have built automated workflows to facilitate and guarantee the quality of that data. As an example, when we do a lot of automated liquid handling, and we use robotic handlers for a lot of things to set up reactions, sample those reactions, analyze them, and measure some sort of response. This is one of our setups that measures solubility. And as soon as a new compound is registered and measured, that data push kicks off an automation workflow where all of the metadata regarding the batch, the source, the ID of the compound are pulled together, merged and indexed, and kick off other workflows such as predictions for further physical properties such as solubility, pKa's, and log P's. By the way, I don't do all of these things. I've got really good colleagues who I consider to be fairy godmothers, and I'm blessed to be able to work with them. And all of that data ends up in a database where it's consolidated, validated, and checked before we can output them to everyone who's asking them whether they are to be interacted with or visualized and reported. And actually, I will be, for the rest of my talk, focusing on how we've done this easy for our colleagues who don't have data or scripting or other digital skills, so that they can use their chemical intuition without having an access barrier to our data. To achieve this, we've employed open source software, such as the package Streamlit in Python language and RStudio Connect, which is a containerized platform to deploy what we call web applications, interactive web applications. We have found that this mode of operation has a lot of advantages, such as flexibility. We can reuse the code, so we don't just make one tool, we make a few tools that have shared parts. They maintain relevance because we can make them do what we want when we want them, and we have ownership with them. Obviously, all of this freedom comes with responsibilities, and those are setting up these tools and maintaining them. We have found that the overhead of effort that's required for these two aspects isn't more than the choice of going with commercially available platforms such as Spotfire or Power BI, which don't really offer all of these advantages. So to show you more specifically what I've been up to as a data and automation expert, I want to show you how we do solvent selection for liquid extractions. A lot of the time in industry, we refer to liquid extractions, and we mean the partition of a material between two immiscible phases, one usually being aqueous and the other being organic. This is a well-established unit operation within industrial processes. Usually what follows a reaction is a workup in the form of a liquid extraction. And this process involves some physical properties, constants such as the dissociation constant and the partition coefficient of the compound between these two phases. All I'm trying to get at is that because of how established it is and because of the known mathematics of equilibrium that are involved, this process lends itself easily to digitization and fast process simulation. So our users are greeted with this sort of interface where you can have different segments and collapsible containers to help your user navigate the interface with ease. And once the user inputs some details, such as a unique compound identifier, they're greeted with interactive plots where you can see the speciation of each compound in the aqueous layer against the pH. This helps cultivate process understanding and allow the user to understand how they can tweak the system. Furthermore, you can choose which of the two layers you want to isolate your compound with, and it gives you some useful information. For example, in this case, you can see that the highest possible extraction efficiency is modest, around 86%, and that can be achieved at a pH around 4. Having inputted the required information, we can see that for this step, the minimum required organic volume is around 60 relative volumes, which is obviously a no-no if you want to run this process commercially. So how can we compare between solvents in a constructive way, such that we can make informed decisions? Well, we've built another container where you can select solvents from a database to compare your extraction efficiency against, and you can do this based on physical properties, regulatory requirements, and get helpful messages as you are browsing your selections. You can also select solvents based on the functional groups that they have, so that you assure the chemical compatibility, and you can choose solvents to either have all of those functional groups or any of those functional groups. And obviously that restricts or broadens your selection. When you press a button to move on, the system can calculate the extraction efficiencies for you. As you can see, in this case, it can run around 12,000 calculations, and it does that in a split of a second. And by limiting your criteria, you can see that you can filter down that number by quite the margin. You get plots that are interactive like this, which you can filter to really allow you to compare between solvents of interest. This is comparing the extraction efficiency against the pH in the organic phase. Or you can compare the extraction efficiency against the relative volume, and again, limit yourself to only those selections that are truly viable for you or that you need to query, and you get helpful indications upon hovering your button. So all of these plots are highly interactive with the aim of putting the data at the fingertips of the chemist so that they can make the right decisions at the time that they need them. You can also download all the calculated data as well as the metadata of the investigation, so which functional groups of solvents were selected, what were the ranges of boiling points and densities, which actual compounds did you interrogate, just to provide context to your results. Again, navigating through this interactive web tool doesn't take more than 10 minutes, and you can really get far with it. For example, here we see a table of the results where you can instantly hone on to at least 3 options of solvents where the purity is more than 90%, with a sensible process mass index value, and that significantly bring down that minimum organic relative volume quantity. So these numbers are obviously based on calculations with certain caveats, but we have found that those caveats are acceptable. They need to be viewed as hypotheses, which are generated and need validation in the lab. And actually, in this case, lab-based experiments confirmed that 2-methyl-THF was the best solvent. And by best, I mean within the context of the optimization that we are trying to achieve. But let's consider what we did here. So we've browsed around 300 solvents. We were able to constructively retrieve data about dissociation constants, partition coefficients for all of those solvents, solubilities for all of those solvents, simulate our process en masse, and go from a potential process that would be using close to 60 relative volumes with a modest efficiency and high residual impurity to a process that was using acceptable quantities of a better solvent, had high extraction efficiency, and ended up resulting with a low residual percentage of impurity. We also managed to expand our pH operating margins, which is always good when you're scaling up in plant as well. At the same time, we generated contingencies for future studies. The chemist interacting with this tool gets more of an understanding of what the process is. They really develop a feel of how they can optimize it, and it's right at their fingertips. They have easy access. They don't need any data skills. They don't need to be scripting in Python or NoSQL, or have special access to a database. They just navigate to a certain URL and are able to access the tool. And from a project perspective, this achieved a 50% PMI reduction for this stage with a projected annual savings of 300,000. So it can be really powerful to use. Now I want to move on to an aspect that it's really close to my heart because it's more philosophical, I shall say, and it's concerned with traversing chemical space, and more specifically solvent chemical space. So you would have seen that late last year, the EPA moved to ban dichloromethane or DCM from the US, and Chemistry World was publishing articles about what would that mean for university labs. But it's not just university or academic laboratories. A lot of industrial labs use DCM as well. It's not just the US. If they did it, it wouldn't be too long before the EU or the UK or other regulators issued similar bans. And what if it's not just dichloromethane? What if it's something else as well? So this begs a few questions that are simple but require complicated answers. And one of them is, what do we substitute DCM with? Which you could turn to, what is DCM similar to, and within what context? And again, is it just DCM or is it something else? So if you had a mixture of DCM in methanol, let's say 90 to 10, would you be able to turn it to a different mixture that would have the same properties or give you a material with the same properties by not using either or at least one of them? How would we do that? And this is where this idea of traversing and navigating chemical space really resonated with me, and decided to work on this. So if you think about it, if you want to move around and you don't know your environment, what you need is a map. And again, I'm really lucky to be working in an organization where people have long before me thought about this problem. So about 9 years ago, good colleagues of mine came up with a principal component analysis of solvents that are used in industry, which is essentially a map in a projected three-dimensional space of all the solvents that captures most of their properties and descriptors. So if we have this information, how can we use it to achieve our goal? So get a substitute of DCM or a mixture of DCM with something else. And again, you can build an interface and you can see how it looks similar to the other, where you can define a solvent mixture and its ratio. You can define its search distance, so how far around me do I need to look to find what I want. And you can also select which solvents to include in your investigation. And I'm sure a lot of you will see that this is similar to the previous tool. This is what I was going on about before on code reusability. It's something that you own and you can port into different things as if when you need it. And by doing this, you can get these beautiful 3D plot where you can have your pure solvent mixtures visualized with one color. We can see where DCM is in this three-dimensional plane, where methanol is in this three-dimensional plane, and somewhere in there is our defined mixture. Our search distance is defined by this sphere of gray dots, and all of those blue dots there are actually points made up by the binary combination of the rest of the solvents that are close enough to the solvent mixture that we are trying to change. And again, we had a lot of combinations, close to 200, but these are a few that resonated with the project, adhering again to sustainability goals and waste on scale. Ethanol toluene, methanol toluene, propionitrile toluene, ethanol MTBE, acetonitrile toluene. All of these are sensible solvent selections, but you would never look at them and be able to go, oh, I know what I'll substitute DCM methanol with, methanol toluene, and you'd never be able to guess their ratio as well. But in this case, we can most definitely do that. So yeah, ultimately, this is the combination that was selected. And yeah, we went from a position of having DCM 9010 to a solvent that was 5644 toluene methanol. Multiple solvents were again assessed, providing contingencies. So if you found that this doesn't work, you could look for a different option. Using the tool only physically took 10 minutes, maybe half an hour, with a discussion about prioritizing which experiments to do. But it only took 8 validation experiments on 10 milliliter scale to achieve this result, which guaranteed regulatory compliance and no change in the specifications of the material. And let me tell you, being able to change something whilst maintaining these two aspects is something that, yeah, we try and do day in and day out, because obviously we are heavily regulated and we're not here to fight those regulations. We're here to abide by them. Obviously, because this is application agnostic, it can be applied to analytical activities. Think about how much solvent we are using on chromatography, for example. Acetonitrile isn't the best solvent, but it's a major component of eluents on chromatographic instruments. So what if you wanted to change acetonitrile to something else, for example, or isolation activities? You have a solvent mixture that you do your crystallization out of, your extraction, or your wash. What if suddenly you couldn't use one of those solvents and needed to change it? And we are actively looking into cases regarding these examples. And with that, I've reached the end, and I would like to emphasize that the selection of solvents is really important and applied to everything that we do in and out. And it might sound trivial, but it's certainly not. I hope I have shown you that data-led investigations can reduce material requirements and the amount of waste that we produce. And we're obviously doing this to assure sustainability. We only have one planet and we need to care for it. And myself, I'm a strong believer in rendering onto chemists what belongs to the chemists. I love to build tools and workflows that work for humans and not the other way around. And I tend to do that by sticking to our values of following the science, being entrepreneurial, and doing the right thing. Last but not least, I'd like to thank my excellent colleagues in computational chemistry. We did a lot of work with Simone and Maxime to be able to merge data into an indexed and curated database. Tabassum and Elliot, who support coding activities. Tabassum was a rotation graduate student. She didn't know any coding, but she immersed herself into it, took the bull by the horns, and by the end of it, she was showing me a couple of tricks as well. And obviously, the good people that look after our database, maintaining. And lastly, you for joining and for your attention. Thank you very much.
Fantastic. Big thanks to you, George, for that excellent presentation. I think you really showed quite clearly the complexity of the task at hand when choosing a solvent, but also the real benefits of using a data-driven approach to decision-making. So we have time for a number of questions. There are a couple on the chat, which we can go to first in the absence of hands. Otherwise, you're welcome to put up your hands and we will get to you shortly. So first question, which I think is from Ellen. George, once a compound has been registered, which solvents are chosen for the solubility predictions performed?
So for solubility, we have two workflows for predictions. We have an informed workflow and a non-informed workflow. So because we want to have data available at any point of development, we have one model for predicting solubilities just based on structure. And I think that involves 172 solvents. I can't remember them all by heart. But then we have another workflow where we do some solubility measurements in 20 solvents, and that information is used to predict solubility using a different model that involves 280 solvents. So at any point in development, whether you have measured solubility data or not measured solubility data, you have solubility data to work with. And we've had cases in the past where that data was really, really good, and cases where it wasn't so good, but you always have the option of measuring the solubility as well.
Great. Next question. What type of model are you using for solubility prediction inside the web app? That's from
I am not I'm not expert enough to answer that. I'm sorry, you'll have to speak to one of my colleagues or reach out to me and I'll be able to put you in contact with them as well.
Thank you. Next one from Ian Underwood. Thanks, George. Did you generate, whoops, everything is moving. Did you generate all the data in-house or was it collected from reference material?
Most of the data on solubility is generated in-house, as well as partition coefficients. But we have processes of consolidating data that comes from commercial obtainment of compounds. For example, if we buy a compound in, or if the solubility is measured at a contracting organization, we have ways of importing that data and making sure that they adhere to the same standards like our in-house data.
Excellent. Next question from Nat Monk. In terms of sustainability, does replacing DCM with toluene go far enough? Do you also need a replacement for toluene for larger scale and manufacturing?
In this case, it did go far enough. I mean, this is obvious, but DCM is heavy, it's quite dense, which means that the larger the volume, the larger of the mass of it you need. So in the process mass index, it's through the roof. So as soon as you substitute it with something else that you don't need, twice more of, you are okay in terms of sustainability. In this particular case, it worked out all right. We haven't explored substituting DCM with toluene as a one-to-one solution. So it might be that for a different application, you would need to retrieve to one of the methanol MTB suggestions, for example. It's just that in this case, that's what worked best.
Okay, next question from Tara Lerche. Are you able to make good predictions for aqueous mixtures as well as organic?
This is a very good question. So unfortunately, our aqueous mixture predictions aren't as good. The current thinking is that we're not accounting for everything that's in the aqueous phase, and we are working on improving those predictions as well. But those would be really useful, because then in the extraction tool, you would be able to define what your aqueous phase is quite reliably as well, because there are a number of ways of fixing the pH within a certain range. There's not one buffer to rule them all, for example. So you want to be able to reliably select that one as well. So yeah.
Okay, lots of questions. Next one, Lyndon Schrecker asks, do you take multi-parameter effects such as solvent temperature effects into account?
We do. So we have a way of very accurately estimating the change of solubility and log P based on very sparse variable temperature data. If we don't have that data, we employ predictions, but we do take those effects into account to the extent that we can. What we don't really take into account is effects between the compounds themselves. But those are definitely non-trivial, or they're less non-trivial than the solvent temperature effects.
Okay, next question from Alan. How do you perform solubility predictions for salts?
Again, not my expertise, and I would defer answer after consulting with my prediction colleagues. I've been in enough physical properties prediction discussions to know some stuff, but not all of it.
Okay, and one more from Ian Duncan. If your validation experiments do not prove out, what process do you use to identify which data isn't correct?
That's a good question. We haven't been caught out yet, but we haven't used these tools so extensively either. We've got about 20 or 30 cases where we've used them, and because our ethos is generate hypotheses and test them in the lab, usually the testing is satisfactory. So for the liquid extraction tool, the measured extraction efficiency was above what the tools predicted. So if anything, we are underestimating it a bit, but we were able to hone into a couple of options that worked really, really well and stood out from everything else. Now, in terms of when that happens, we will have to investigate. I'm assuming that things can go wrong again if you have a high amount formed of one impurity, but in that case, you would have to scrap the whole process altogether because you would need to optimize the reaction itself before you optimized the workup. I hope that makes sense.
If not, I'm sure we'll get another question. Next one from Andrew Bird. Nice talk. From a software side, I was wondering if you had any issues using Streamlit with large numbers of users.
Again, we haven't yet. We are hosting Streamlit on RStudio Connect containers on our scientific computing platform. We can have, I set the specifications for the containers, and I think I've said that something as 100 connections per instance, and we haven't hit that yet. So they haven't cut out. And again, because connection can only be obtained within our own intranet, it's not like people are constantly connecting to it. Another aspect is that you don't need more than 10-15 minutes to use the tool to get something useful out of it. So it's not that people are connecting to it and staying connected on it. They can very quickly get out of it what they want.
Okay, so those are all the questions from the chat at the moment. Any last questions from any of the audience? In the meantime, I'd like to encourage you to register for our next webinar on the 25th of February. I've posted a link in the chat. There are also a couple more lined up for March and April. I will post some of the info on that. And I guess in the absence of any other questions, thank you so much, George, for a really interesting and useful talk. Solvent selection may sound like a relatively trivial and maybe boring issue to many people, but anyone who's developed a process knows that it can be super critical to many, many things. So I think it was quite an eye-opener, and the really data-driven approach was super impressive as a way to make sure that you're covering all bases and considering all options. So thank you, everybody, and we hope to see you next month. Thanks for the great turnout.
Thanks for having me. Have a nice day.